Okay, so we're recording. All right. Good afternoon. We are starting a review of material in sections in chapter 3 and 4, which is sets and functions. Okay. Here is the basic terminology on sets. A set is an unordered collection of items, and we denote it with curly brackets. So here is an example of a definition of set S as a set, and you know it's a set because it starts and closes with curly brackets, set of 4 elements. These elements are A, B, C, D, 4 letters. Okay. So the order in which we list elements of sets don't matter. So sets are unordered collections. So if I say that my set includes integers from 1 to 10, it doesn't matter what order it includes them. There is no notion of ordering when you talk about sets. It sort of matches what the way we use it in English, right? We say it's a set of people who take a class, or it's a set of professors in a department. There's no implicit ordering of them. It's you either belong to a set or you don't belong to a set. That's the only thing. There is no notion that you're like 3rd or 5th in a set. That an item is an element of the set is designated by a special symbol, this kind of E-like symbol. It reads B is an element of S, or B is a member of S. Okay, it's a set membership symbol. Okay, and if I want to say that something is not an element of S, so for example here, little e is not an element, I designate it by a membership crossed out. Okay, so similar, you have the similar notation, like for example, equality. And if you want to say that something is not equal, you take equality sign and you cross it, right? It's the same convention here. You could have sets that have infinite number of elements. Like, for example, it's a set of all integers. Or you can have finite sets, like, for example, a set of students in a class. Okay. If S is a finite set, then I can denote its cardinality by 2 vertical lines before and after a set. Okay, so this is read the cardinality of S, or simply the number of elements in S, because the cardinality is the number of elements. Interestingly, you can also talk about cardinality of infinite sets. And so the cardinality of integers is a special name in set theory. It's called Aleph 0. And the very funny thing is that infinities are not all equal. So you can prove that the cardinality of, say, integers is actually the same as cardinality of positive integers, which is weird because it seems like, well, what about the negative integers? Shouldn't there be more negative integers than just positive? But in fact, because you can write a one-to-one correspondence between these two sets, they have the same number of elements, but it's an infinite number, so it's not a very, it's a counterintuitive notion, but actually it's not so hard to see what that would be. And even stranger, rationals also have the same cardinality. But once you jump from rationals to reals, you can prove that they cannot have the same cardinality, that reals have strictly larger notion of infinity than all the ones before. So all the ones before, naturals, integers, rationals, are called enumerable. Everything that has the same, in a sense, elements as naturals are called enumerable sets. And in some sense, discrete mathematics deals with enumerable sets, things that I can list, even if the list is infinite. But there is more, and the totally natural thing, reals is strictly more, and this is kind of like the border between discrete math and continuous math too. Its rationals are not continuous because there are some, well, it's funny, like in every interval, I always contains rationals, and in fact contains infinite amount. And no matter how small you get, there's always a rational inside. And yet there are gaps because there are numbers on the line, like a pi. It's not rational. Okay, so that's where continuous math kicks in, and you can see that by looking at the notion of cardinality, that reals have more. There's more elements, like in some quantifiable and qualitative way, more. Okay, so a little detour there. You can look at Wikipedia, like how do you count cardinality of infinite sets? So here are the sets I was talking about, natural numbers. These are numbers from these are integers that are non-negative, from some 0 up. Some people say naturals is from 1. We are going to say naturals are from 0, and that's a more modern convention. Although it was not always the case in history of math. Z is the special symbol that, so we use this like N with a bolded bar, or Z with a bolded bar. Q, when you write it, you make a line, vertical line, extra line. Z is the integers, so naturals and their negative inverses. Q is rationals. So all numbers which are formed as C divided by D, where C and D are integers, except for the denominator equal to 0. Okay. So here is the reals. Okay. And here is the special another famous set. That you should familiarize yourself with this notation. You know, you should recognize it. When we say X is in Q, that means X is a rational number, or X is in R. X is a rational number. This O crossed out is a special symbol denoting an empty set. Another symbol for the same thing is this, open and close curly brackets, because it's a set and there's nothing in it. So that's an empty set. I'm looking at some chat messages, but I actually don't see anything. So, all right. It's like I cannot read that fast, but it doesn't look like there is a question. All right. Another common sets we will consider. So we'll say that if you have a domain of any numerical domain, integers, rationals, reals, you can restrict it by considering only the positive members of these sets. In other words, those greater than 0, or negative, or the same plus a 0, which is non-negative, right? So it's positive plus a 0, or non-positive, negative plus a 0. We denote these sets with plus or minus in the in the superscript. So for example, z plus is positive integers, z minus negative integers, etc. Okay, so this is again a notation that you should be familiar, because I would just say n is in z plus, and you should know, okay, n is a positive integer. Okay.
How do you say the non-negative then?
You don't. Just say z plus union 0. Yeah, I don't know any notation for that. Good question, though. If you see some notation out there posted on Piazza, I'm not familiar with it. Specifying a set. So you can, well, the notations that you've seen for how to specify a set is open curly brackets, list elements, close curly bracket. It's not like a perfect notation. So because if there is a lot of elements, then, well, you can either maniacally list them, right? But it would take you a long time. Or you can maybe use like ... notation, meaning that the reader is going to infer the pattern, right? Like, so for example, here, probably, you know, a session reader can deter a pattern that these are odd positive integers, all of them here, those until 99 here. But, you know, sort of detection of patterns is an imperfect skill. And, you know, here, for example, it is the case that these numbers happen to be all integers of the form that are equal to n squared minus 1 for some integer n. Okay, so this is, you know, 4 minus 1, 9 minus 1, 16 minus 1, etc. On the other hand, you know, this is a good example that, like, you might not see this pattern, and I wouldn't blame you. So here is a set builder notation. Lets you avoid this type of imprecisions. You open bracket with curly sign, so you know that whatever is inside defines a set, because if you open and close curly bracket. But the way you state elements is like this. You're going to call these elements x, and this is arbitrary. It could be y, it could be z, it could be n, whatever you want, some variable. I forgot what this symbol is called in English. Yes. Okay. Sorry, I forgot.
Colon?
This. What's this?
Is it just a colon?
Colon. Yes. Thank you. Thank you.
No problem.
Thank you. My ignorance. Colon.
Okay.
Yeah, I should know. Semicolon. Colon. Good. So, a name of a variable, colon, and then it is read like this is a set of all x's. This is the colon is read such that x belongs to some set. Now, this is self-referential, because if I just write this, then if S is defined, this is just a redefined set X, S. But however, I can add Boolean expressions here that would basically, for example, say X in S, and some predicate is true about X. Some Boolean formula is true about X. Some, you know, some numerical conditions are true about X. So even more generally, we use set builder notation like this. On the right-hand side, we'll have some condition on some variable. So all x that is in some set and meets some conditions. But the way we will use this variable to build elements of this set is that it's not just variable values by itself, but values of some function on these. Okay, let's look at an example, okay? Because this is maybe too abstract. I'm very sorry, but I guess I'm getting a phone call, but I don't even see where this is happening. So Okay, do you guys see the slides back? Okay, I hope you see the slides back. So,
Professor?
yes.
So would you say that, just to summarize that last part really quick, basically anything after the colon is essentially like the subsection of this, of like you're saying, so within X, let's focus on this piece of it after the colon. Like anything after the colon is saying focus on this stuff within that X,
okay,
for example?
You know what, like this is abstract. Let's look at examples, okay?
Sure.
And then maybe we can generalize from these examples. Okay, so for example, here is the first set definition. I'm defining a set of elements which look like n squared minus 1, where, I guess I would read this now, where n is a positive integer. Okay, so this defines this thing. In other words, a set of all integers of the form n squared minus 1, where n is some positive integer. So what's going to be in this set? 0, because for n equal 1, you get n squared minus 1 minus 1, 0. 3, if you instantiate this with n equal 2. 8, that corresponds to n equal 3, etc., right? So as I range over all positive integer n's, each of them is going to give me some numerical value here, some integer, and that integer is declared to be an element of this set. So it's a set of all values of this form. That's how it's read, okay? Again, if I say S equals this thing, I say S is a set of all values of the form n squared minus 1, where n is a positive integer. Another example. Here is a set of all n's such that n half, so half n divided by 2, is a positive integer. Okay, so I can actually equivalently define it as all sets of values of form 2n, where n is a positive integer. You can check that this defines the same thing. In other words, both of these will define even positive integers, right? Because what kind of n is there such that n half is in z plus? Well, what's the first thing in z plus? 1. So what n gives you that n half is 1? Well, 2. Then the next integer 2, right? So n would be 4, and you would get a 2 here, etc. Right? Like, so to get a 3 here, you would have to start with a 6. To get a 4, you start with an 8. So this set contains 2, 4, 6, 8, and you can convince yourself it will contain all even positive integers. We can mix basically some function of n here with some condition how it is defined, right? So let's define a set of all elements that look like 2n, where n over 3 is a positive integer. You can see that this divide creates these numbers. Basically, it's a set of positive integers divisible by 6, right? So the smallest number that like this is 6, right? Because it's 2 times 3. 3 divided by 3 is the smallest positive integer. And so on and so forth. Not the most natural definition, right? Like I would define the numbers divisible by 6 using a notation, for example, like this, open bracket, 6n, where n is in z plus, like this. So instead of here, I will have 6n, right? And it would define, again, the same set. Or I can use this form, n or n, such that n over 6 is in z plus. It's a mixture. It's not supernatural, but anyway, that's what it defines if somebody wanted to use this. Here is, again, a set of values of the form n squared, where n is such that n over 2 is an integer, a positive integer. Okay, so it's a set of squares of even integers. Okay, we will use these notations, a set builder notation. So, for example, I didn't have, these were not examples where I had explicit condition expressed in some Boolean formula, but you could. I could say it's a set of all elements of form n square such that n over 2 is in Z plus and 2n minus 3 is in Z. Okay. Okay, I guess that's always true. So, you know, n over 5 is in Z. Okay. I could have a Boolean formula here, and you'll see such examples too, also in book exercises. And so, okay, a little maybe abstract, but okay, hopefully it just became clear. If not, let me know. Here's a relation between sets. It's a subset relation. We denote this relation with this symbol, and it's read that set T is a subset of set S. This should not be confused with a belong member of notation, right? So this does not say that T is an element of set S. It says that it's a subset. This relation is defined as with the following statement. T is a subset of S if and only if, for all x's, the following implication holds. If x is a member of T, then it must also be a member of S. If this implication holds and is universally quantified, then we say T is the subset of S. And why is this? So look, this is a pictorial illustration. These kind of pictures are called Venn diagrams, where you describe sets pictorially, and all you show is what's the relation between them. So here is a Venn diagram of the relation that T is a subset of set S. And what this implication says is that whenever every element of set T must also be an element of set S. So therefore, you can write T inside of S, right? Because, you know, let's say there's hundreds of elements here. They are form set T. They are also members of set S by this formula. To show that T is not a subset of S, all you need to show is a single element that contradicts this statement, right? So how to contradict this? You have to show that there exists an X that violates this implication. Now, how do you violate an implication? You have to satisfy the first and fail the second, right? So you have to satisfy the hypothesis and fail the consequent. So you have to find at least one X, and actually one is enough, such that it belongs to set T, makes this hypothesis true, but it does not belong to S. So therefore, consequent is false. Therefore, this formula is false for this X, and all you needed to violate is a single X like that. In other words, a single element X that is in set T, but is not in set S, right? So it's somehow outside. Here is some example. So S is ABCD, T is ABC. And set T is a subset of set S, right? Because if you look at the universal quantification, no matter how you instantiate X, if X is a subset, is an element of this, then it's also an element of that, right? So if you instantiate X with A, it's true. It's here and it's here. With B, it's true. With D, It's also true because this part is false. So implication is true. With anything outside E, F, G, H, this part is false and this part is false, but that is okay. Implication is still true. Okay. Now V is a set like this, and V is not a subset of S, right? E is a counterexample. E is the only element here for which the implication would fail, right? Because E is a part of V, but it's not, so it will satisfy the hypothesis in this implication, and it will fail the consequent. Okay. Okay. And well, also V is not a subset of T. We can relation between sets of the subset relation between sets, right? Like the fact that naturals are a subset of integers and integers are a subset of rationals and on, right? This relation corresponds to Boolean operation of implication. If you are in one, then you are another. If you look at the set builder notation, you can basically build a set using a predicate. You say, this is a set of all x's such that arbitrary predicate on x holds. If you define some predicate, then you immediately define a set of elements that satisfy this predicate using the set builder notation. Next time I'll have like, and now I see that I already need like a little piece of paper so that basically simulate a whiteboard so to tell you like these extra examples. Predicate immediately defines a set. An implication that if some formula, some predicate is satisfied for x, then it's also satisfied some other formula. So let's say if P of x is true, then Q of x is true. That is in terms of sets which predicate P defines and predicate Q defines, that is a relation of subset relation. All people who satisfy predicate P are subsets of people who satisfy predicate Q. So the set related to predicate P of all elements that satisfy it is a subset of elements that satisfy Q. That's what you're saying when you're saying that P of x implies Q of x. Okay, but that's an implication. Let's now look at other Boolean operations, and they are one-to-one with operations on sets. And the notion of predicate and a set builder basically jumps you from predicate was something about Boolean expressions, right? But actually it's a set of all elements that satisfy the predicate. And that correspondence between Boolean operations and sets is gonna carry. So what? If I have some two sets defined, and think of those as defined in terms of some predicates. Set A is defined as like all those that satisfy some predicate connected to A. B is all those that satisfy predicate connected with B. I define a union of those two sets as all those elements that satisfy a disjunction, an OR expression, over these two predicates. So X is in A, in other words, X satisfies some predicate associated with the set, or X is in B. Okay, so if these are my sets, then Venn diagram for a union will be all of them combined, right? So anybody who is in A, anybody who's in B, and also everybody who's in both. What does that, by the way, correspond to? That everybody in both? That's a reappearance of the fact that the disjunction is inclusive. It's okay to be a member of both sets, to be in their union. Okay, very natural notion. Like once you start thinking of unions, then of course you don't kick out people who are in both, right? So a union of ICS students and ICS students and math students definitely don't kick out people who are in both, right? That would be crazy. So you see that the union is very natural, that it's inclusive, and that's part of why we define disjunction as inclusive. Intersection corresponds to a conjunction of statements. Intersection of two sets is a one-to-one relation with a conjunction on two predicates. That first, the predicate that you belong to A is true, and the predicate that you belong to B is also true. Then we declare you a member of an intersection of the two sets. So in terms of the Venn diagram, it's everything that is in purple, right? Like it is both blue and red. Set difference is not a super natural Boolean operation anymore. It's a conjunction with a negated. Okay, so this A subtract set B is, in terms of Venn diagram, is this shape. It's everything pure blue. So you kick out those in blue, which are also in red, right? So in other words, it's a conjunction of you are in the set difference if you are in A, but also you are not in B. Okay. By the way, in the book, this is written with the same minus that is used for integer operations. So a set difference, some people designate with a minus sign, just like 5 minus 3, like integer difference. And others designated with this notation. Okay, so I will use this one in lecture. The textbook uses minus. They designate the same thing, and you should be familiar with both, because indeed both of them are used out there. Okay. Complement is one-to-one with a negation. So if set A is defined with some predicate, and by the way, so I said predicates define sets, right? A set can be defined. If you have a predicate P, I can define the set of all elements X such that P on X holds. The predicate P holds about them. But likewise, there is a move the other direction. Once you have a set, you have an immediate predicate. What's the predicate? The predicate defined by a set is that X satisfies the predicate if it is a member of the set. So every set has a natural predicate connected to it. The predicate is, again, it holds about X, even only if X is a member of the set. Okay? So whether you think of the predicates or sets, you can move back and forth. Complement of A is defined as all sets of all such elements that this predicate is satisfied, which is that you negate inclusion in A, right? So all elements that are not in A. Now, for this to work, you have to have a notion of implicit domain, because when I say it's a set of, it's a complement of the set of ICS students, then I say, well, it's all UCI students who are not in ICS, all students in the United States which are not at ICS, in who is not in the set, right? So I have to have a notion of implicit universe from where, like the borders here of the universe from which I exclude this A set, okay? And everybody in the black part is now in the complement, but how far this black part goes, right? So we will usually have some notion of implicit domain, right? Like it will usually be, and we will, if it's important for exercises or tests, we'll say the domain is this. assume the domain is reals or domain is integers or positive integers or what have you. So the notion of complement is sensitive to the implicit domain. But then there would be implicit domains that are kind of immediate, like you would know that like this is all about integers, or you will see that this is all about reals, or you will see this is about students at the university, etc., etc. Let's look at some of, examples of operations on sets. A is a set of all odd integers, right? So using set builder notation, set of all x's which are in the that's actually yet another version of the set builder that I didn't use before. This is because I never had the inclusion before the colon. The way this is read is all x's inside z such that some predicate. So here x is an odd. B is a set of all x's which are in integer set such that x also satisfies this predicate. X is between 0 and 10, but this is strict inequality, right? So it's basically from 1 to 9. And here is some set explicitly defined, right? 4 elements. So let's look. Intersection of A and B. So it's all who are in set A and also in set B. So it's all integers in both cases, such that first of all, an integer must be odd, and second, it must also satisfy the B set predicate, which is that it is between 0 and 10, or really between 1 and 9, right? So which odd numbers are in this set? Okay, here's a cheat sheet, right? The intersection is a conjunction of these two predicates. So it's satisfied by 1, 3, 5, 7, 9, right? These are all the integers that satisfy the A set predicate and also the B set one. Let's look at this. So intersection of C with the complement of A. Well, we can assume the universe as Z, but in fact the answer would not really differ, because like if this was real, it still doesn't matter. You have to take everybody not in A and intersect it with C. So the only thing you care is, you know, whatever universe that includes these, all right? Because in any event you're gonna intersect them with these guys, right? So it's not in A, so therefore it's even, and intersected with this basically kicks out 5 and kicks out 7, right? So that's only those two, 4 and 6. Is C a subset of B? Yes, it is, right? Because for every integer that satisfies this predicate is member here, it also satisfies this one. It's a member of B. Is B a subset of A? No. Not everything that is in here is also in here, right? So there is numbers that satisfy this predicate but do not satisfy this one. There are any even elements in this range. So 2, 4, 6, and 8. Is 6 in the complement of the union of A and C? So let's see. Union of A and C. A is odd integers. C, we have some odd integers here, so they don't matter. They don't really add anything to the union. But 4 and 6 do add, right? So A union C is odd with a 4 and a 6 added. Complement of that will not include 6 because 6 is part of the set. Okay, so it's therefore it's outside of the complement because that's even on here. If you are a member, then you are outside of the complement. If you are not a member, you are in the complement. What about 26 in here? Well, let's see. 26, is it a member of A union C? It's not a member of C. So let's see if it's a member here. It's not, because 26 is not odd. So 26 is not here, not here, therefore it's not in a union, therefore it is in the complement. Okay. All right. Power set. So another concept. Power set denoted P of set A is denoted P in brackets of A. And if you know that A is a set, then you read this notation as the power set of A. Okay, so here is what is it? It's a set of all subsets of A. So if set A, for example, has elements ABC, it's a set of 3 elements. What's the power set of A? How many subsets are there, distinct subsets of A? Well, first of all, an empty set. Empty set is a subset of every set. Why? Because the implication that if X is in here, then X is in here, trivially is true, because for every X is never here. And implication is true if the hypothesis is false. Yes, so that implication is always true, and that's intuitive. An empty set is a subset of everything. It's this little empty thing that you can always stick in, and it doesn't really change, right? For example, you can convince yourself that A union empty set is A. Okay, so an empty set is a subset. Subset, which this is a set that includes only one element, an element A. This set, it's a kind of a trivial set, and it's like a little bit hard to think of it as a set, perhaps. It's a set that has only one element. This set is called, it's because these kind of sets are funny, and we call them singletons, sets which contain a single element. These 3 are all singletons, and each of them is a subset of the set, because again, the implication that if something is in this set, that something is in here, well, that's true. The only place where this implication is non-trivial, if you instantiate the something with A, then the A is in here, and it's also an element of set capital A. That implication will work for these singletons as well. Here are the sort of non-trivial subsets, right? Like a subset of A that is made of A and B, but not C, A and C, but not B, etc. And here's a subset, which is the full set. Again, it is true for any set A that A is its own subset. It's called a trivial subset. So the minimal subset, empty set, and the maximal subset, the set itself, these 2 are both called trivial subsets. They always exist for any set. Singleton is a set that has only trivial subsets, empty and its set. It doesn't have any further subsets. But a set with more than 2 or more elements will contain something in between an empty and a full. So power set is a set of sets. Elements of a power set are all sets: a trivial, empty set, full set, singleton sets, and anything in between. But elements of the power sets are sets. One thing that as a computer kind of person you can think of, like, what's the difference between sets and elements? Think of arrays or records. Basically, an array that contains only one element is not that element. It's still an array which happens to contain only one element. Or a record that contains only one, right? These are all, if you equate an array with a single element, you're going to have a type miscast and your code will fail. So a computer programmer will recognize the difference between a data structure that happens to have only one element and that element. Okay, so a list that contains a single integer 1 is still not equal to just integer 1. And if you try to program and say like the list is equal, you will have a type miscast. Okay, is this set a member of the power set? And yes, it is. It's here, right? It's if you. I used the enumeration convention for defining a power set of A. Curly brackets, and what's inside are elements of the power set. And this set is an element. It's listed here. Is A and B a subset of the power set? Well, let's check. Is it true for every x that if x is a member of the set, then x is a member of the set? What does it mean that x is a member of the set? Well, there's only two cases of interest, x equal to A and x equal to B. Both of them will fail. They're not members of the power set. A is not on this list. A singleton set whose only element is A is on this list, but it's like an array whose only, it's a list whose only element is that one number. It's not that one number. It's not the same. And likewise for B, set whose only element is B is on the list. B itself is not. Is A an element of the power set? Is A a member of the power set? Again, by the same logic, precisely this is what we're arguing. No, right? Is a singleton set whose only element is A member of the power set? Yes, it's right here. Is a set which is a singleton, whose only element is the set, which is a singleton whose only element is A. This thing is a set whose only element is this little set inside, the singleton set. Is this set a subset of the power set? Let's check the implication. Is it true for every x that if it's a member of the set, then it's also a member here? Well, it's easy to check because there's only one member of this set. It's a set builder notation with a single thing in it. That single thing is this singleton set. That's your x. And is that x on this list? Yes, it's here. So this is a yes. Okay. In fact, it's a yes already by this, right? So we already established this, and we can just hook up to this fact by checking that this implication is true. The implication that is right, because subset notation stands for an implication that says everything that is a member here is also a member of the right-hand side set. Is 0 a subset of the power set? 0 is a subset of everything. So you don't even have to check. You don't care what's on the right-hand side. It could be a most bizarre thing. And 0 is, sorry, not 0. Empty set. This is red. Empty set. I take it back, not a 0. Empty set. I misspoke. Is a subset of any set out there. Including, by the way, an empty set. An empty set is a subset of an empty set. Right, and you can check that the implication works. It's true that for every x which belongs to an empty set, x belongs to an empty set. Is an empty set also a member of the power set? And that's a yes, it's right here. Okay. I guess this is a good place to stop. So, we have power sets. Basically, the next thing I want to look at is ordered objects, sequences, and let's just do them on Wednesday. Because I have a few slides about them. Okay, so let me open for questions. Not that we were closed exactly for questions before, but now, okay. Go ahead.
Professor.
Mm-hmm.
So you mentioned that empty set is a subset of any set, correct?
Yes.
But my question is an empty set a proper subset of an empty set?
No. Anytime you have A is a subset of A, it's always true, but it's not a proper subset. So proper subset is defined as it's a subset which is not equal to the full set. So that's a proper subset concept. A is a proper subset of B if A is a subset of B and A is not equal to B. That's the proper subset. I forget whether the book defines proper subsets. Probably it does. More questions? That's another thing. That's of the general thing that I don't have. My slides will sometimes have more stuff than in the book. Some other examples, some other tangents, and it will also not have certain things in the book. So the book might define a proper subset relation, and I haven't in lecture. It doesn't mean that you are not supposed to be familiar with it. Like the book has more examples of certain things. I cover only one example, and the book has way more and different forms. And perhaps the book has some form which never occurred in the examples on the slides in lecture. It doesn't mean that that this form is somehow out of scope. How far did we get in chapter 2? It's chapter 3. So we are chapter 3 set. I cannot tell you how far we got. Like I would have to look at the book. I think we did most of it, but I'm not sure. It's all in chapter 3, and functions are in chapter 4. There's some on the syllabus. I'm saying there's some sections which are not strictly. You don't strictly need to read them right now. There's no exercises on them. We skip them in lecture, and but you will still be responsible. So you will still be like asked explicitly later. And by the way, this background material that we are needing here, that's in that last section of the chapter 2 or chapter 3 that you skipped at first. So you could just as well read it straight away. I guess if you're completely pressed for time right this moment, then you can postpone it. It's on the syllabus. Okay, guys, and everyone, I will stop recording, and I will see you on Wednesday.